Greetings. Welcome. So I'll just show you where we're at now, where I'm at now, royal we. And everything seems to be coming together. So I'll show you where we're at with that, and then in the last part of the video we'll have a little bit of discussion about how much you might expect to be able to get back from the spike at different speeds for your rotor and at different pulse widths for your pulse. And then in the next video we'll look about adding mass and taking mass out and seeing what happens with the rotation speed. Okay, so here's where I'm at. Okay, so after I got some more PLA, I was able to fully print the penny roll rotor. So here's the finished one, and here's that one. You can see it almost made it, and then I ran out of PLA. That's what it looks like that. So the first thing is going to be to put in the ball bearing, and I want to pick one that I think I haven't used before. You can see there's a little super glue on that one, so that one came out of somewhere else. And I'll mention a couple things. First is that these Yellow Jacket Venom skateboard ball bearings, these are the best ones I found. These things just roll really well. The other ones are all right, but these are better. Now the second thing, this is a little trick that I came up with that usually works, is that if you get the diameter just exactly right to the outside of this, you can press it in from the top, but on the bottom, I don't think you'll be able to see this, but I can feel it with my finger. There's just a tiny little bit of excess PLA on the first layer that kind of got mushed up against the print plate there, and there isn't that on the top. So if everything goes well, what you do is you push this in here, and then you just push it down to the bottom, and now you have it perfectly level and it doesn't want to come out. Now if I was really going to spin this fast, I'd put some super glue on there, but I don't like doing that because you see how snug that is, and you need it that snug or else it'll start wobbling when it's spinning. And you put any super glue on there and it has a lot of vapor to it too, and if any of it comes up and gets in there, then it screws up your ball bearings, and it's now super glued in, and so it's just what do you do then? You got to start over, and you got to throw this out and you got to throw that out. So this would work. I mean, if I was trying to spin this at like 5,000 RPMs, I think I would probably try to glue it in, and usually you can glue it in without a problem, but that's just a little thing I've come up with. So I don't know if I'll use this base plate. I may, but this is just, you put it on here, there's just a little tape there, give it a spin, and it looks pretty good. There's not much of that at all. And this thing is entirely empty, and look at how well it spins. There's next to no mess. That's why I'm saying those Yellow Jacket Venom skateboard bearings are really good. So the next thing is you need to put the magnets in, and I want to use ceramics as opposed to neodymiums this time. And so here I've tripled up these 3 1-inch by 0.16-inch ceramics, and let's see. Yep, they fit, and I don't think there's really any wobble to them. There's a little bit of space up top there. I'm going to do another thing that's crazy. Well, I don't think it's that crazy. I mean, again, we're not going to run this thing like real crazy. I don't think I'm even going to glue these in because it's going to be spinning around like that, and so the force is going to be out like this, and as long as I remember to run it in a traction mode, then the magnets will get pulled down by the electromagnet. If I accidentally run it in propulsion, they might all just go flying off and whatnot. In a moment, though, we'll consider how fast they'll be flying at different RPMs, just to make sure they're not flying at like 120 miles an hour where it would be deadly, but they won't be at the speeds we're running at. Then I have a bunch of copper pennies that I've had for a long time, just kind of importing them over the years. And if we put those in here, that also brings up, see, they fit perfect. And you could even just put it up to there and then not glue those in either. Just as an aside, that brings up another potential Grok video, Grok and the Coin Collection. That didn't go so well. Grok just started making stuff up. I may, if I get a chance, mention that one to you as well. Make a video on that one. So this, everything's good. These fit, those fit, this fits, it spins fine. And so we put all these in and we run it and we see what the RPMs are at a specific voltage. Then we put a load on it, see what the RPMs are, then we put the extra mass in and do the same thing. So how are we going to do the spinning part? Well, for that we need an electromagnet. And I've wound one here with a ferrite core. I would have been done with this sooner, but I actually kind of took a little bit of an unnecessary detour where I was trying to put the coil former together for this, and I spent hours, first designing it and then printing it, and then it wasn't quite right, so I had to print it again, and I was going through all this effort to get this so it slipped right in there. And if you can see it, there's like a little bit of a shelf there, fit the other one on, and it actually works really well until I realized, you dummy. That's only necessary if you have an air core. You can just wrap it around here. And so all you got to do is print, as I've done a bunch of these. Let's see if I got a good one there. It just snaps in, and then you glue it. Put some super glue on it, snap it in, snap on the top, and you're done. And I couldn't believe I had such manure for brains. I got like a, for that part of shop class, that's like an F. So it wasn't just the time wasted. I was just like, I can't believe I wasted all the time on that. But this is actually easier to do and better. And then you just wind a coil like this. We're going to need 2 of these. I've only got 1 wound at the moment. And so this will be where you'll pulse when it comes past the electromagnet. Now I said we need 2 of these. We're not going to run 2 of them as drive coils. We're going to have one as a drive coil, and then I'm just going to use an identical one. And this will be running up here like this, and so just put the other one there. And you could run it through a bridge rectifier, see what you're getting out. The easiest thing to do would be just to short it. And with it shorted, it will provide a constant resistance and a pretty significant resistance. And that way you can see whether there's any change with or without mass when you have that second coil in with it shorted and the resistance that provides. So I'll need to wind the second one of these. So as we want a pulse motor, the last part is how do you get a pulse into here at the right timing for it to, well, in this case we'll run in traction mode to pull this in and then shut off and let it leave. Now the way John Bedini would do that with his simplified schoolgirl circuit is have a second winding of thinner wire called a trigger winding. And when the magnetic field came past, it would induce a voltage in the trigger winding that would be sent out to a transistor, the base of a transistor, and that would turn on the base and allow power to flow into the power windings. Really very clever. But I gotta be me, so I'm gonna do it a different way, and I'm gonna use a Hall effect sensor. So there are all kinds of ways you could get the pulse at the right time. I mean, you could literally just have a reed switch and the reed switch connected to the battery and put the reed switch in the right place. There are problems with that I won't go into. An improvement on that would be the reed switch. You can set it up so the reed switch is triggering the base of a transistor and then you can throw more power in here without worrying about frying the reed or it, becoming a problem. You could have a physical relay with brushes. That would work. You could have an opto triggered transistor. I think I'm blanking on it. Opto transistor, something like that. Then have like an LED in the right place to trigger things. There are all kinds of different things you could do, but the Hall effect, you see that if we go again back to Bedini with the zero force motor has a Hall effect. The window motor has a Hall effect. So I found the Hall effects. I was saying I hope I didn't lose them, but you can see how small they are. And so how are we going to use these to make the thing go? And so we got this here. None of this matters. This is just something I was working on. All we're going to need is one switch, right? We aren't doing any kind of bipolar commutation or anything like that. We just need one switch, and I'm going to use opto-isolated relays for the switch to turn on and then turn off. And the way we're going to get the timing is we'll take one of these Hall effect sensors, which are linear or ratiometric. And what that means is you can have Hall effect sensors that just respond to, say, a north field, and if a south field comes by, they don't do anything. And then you get some north field ones, some south field ones. If you get one of these linear ones, or ratiometric, it'll, as baseline, and you put it, so you hook this up to the analog digital converter chip. And if I get confused on how to do that, I mean, if you get confused, I'm the Grand Poobah. If I get confused on how to do it, I have a previous video, but it's not that complicated. So you hook the Hall up to the ADC, and with these at baseline, it depends on the exact one, but it'll spit out a number, say like 240. And if it sees a south-facing field, it'll go down towards 0. If it sees a north-facing field, it'll go up towards 480 or something like that. So that's the idea there. And then you just use the Arduino code for a single if statement. Say if the value is greater than, say, 300, turn this switch on, and when it goes less than 300, it turns off. So now you have, when it sees the magnetic field, it turns on and then it turns off. Very nice. The one thing you have to remember, which is taken care of for you automatically when you have a trigger winding, is you want to put the Hall effect at about 22 degrees offset when you're running it in a traction mode. And you can run it in different ways. You can run it top dead center, but this is the best way for a pulse motor, as I understand it, about 22 degrees offset. And with the Hall effect, you can examine the different behavior at different places. But that's all there is to that, right? Oh yeah, the other thing, and we'll wrap up the video just doing some back of the napkin calculations, some of which I found kind of interesting. But if you have the sensor, and let's say that you coded it to say, turn this switch on when the value reaches 300. If you put the sensor right there, it's going to be on for longer than if you put the sensor there. And so by moving the sensor, you can do pulse width modulation, which is just a simple way of saying how long the pulse is. And that changes the duty cycle. Now, the other thing you could do is you could leave the sensor, say exactly 1 centimeter away, and in the code you could either say turn on when this is at 375 or turn on when this is at 290. And if you said 290, it would have a longer pulse width, and at 375 a shorter pulse width. And the way people would do that in the olden days, which thankfully I don't even have to worry about. Although, you know, maybe there were benefits and are benefits, but with a trigger winding, you would bias the base, as I understand it, of the transistor to do the pulse width modulation. So let's just put this coil on the LCR meter, and you know, it's got the ferrite core in there now, and there's a couple things that I'd point out, and as I said, we'll just do some back of the napkin calculations, some of which were kind of surprising to me, in fact, and then wrap it up. The first thing, I mean, why did I use 24 gauge? I have no idea. I don't know what gauge of wire to use. The thinking is that if I used like 16 or 18 gauge, then if I was at like 5 volts, the thing might be spinning at 1,000 RPMs, and you have a 0.6 volt droppage across your diode. So if you're running at 10 volts and you have the 0.6 volt droppage across the diode, you lose 6% of your spike. And if you're at 5 volts, you lose 12%. And if you're at 20 volts, you lose 3%. So it'd be nice to run it, you know, at least at 12 volts and ideally at like 20 or 24. It might not sound like that much, but you know, let's say you have a spike that's super, like you get 90% back. If you're losing 6%, then it's only 84% efficient. If you're losing 12%, it's only 78% efficient. If you're at 20 volts and you're losing 3%, then it's 87% back. So 87 versus 78% back. So it kind of is a little bit of a big deal. So that's why I went with the thinner wire. The other reason, you know, there's always just so much variability. Now that we don't have an air core, the Q factor of this coil will change depending on how much current is being applied to the core. I don't think that's going to make a difference. I think it's like if you're really hitting it, you know, with like 2 amps or something, and it's saturating the core, then the Q factor really starts to go down. But before that, as long as there's still some domains that can flip around, I don't think it makes a big difference. But in general, as I understand it, the more amp turns a core sees, the harder it is to have a high Q factor. Now, all that said, I put this on here, and let's forget about resistance. We want to get to okay, so the induction is 91.2 millihenries. Running it, no, you can't, it's not focusing. Oh no, what do we do? I'll have to tell you. It's at 1 kilohertz. Now you can see it. So at 1 kilohertz, it's saying it's a Q factor of 45.7, and that's not bad. Now, so what I've been doing is we can go in here and fiddle around. Let's set it at 2 kilohertz. 2 kilohertz, it's saying 677. Now, I think this meter is, shall we say, overly optimistic. If we go to 3 kilohertz, I don't think it's that good a Q factor, is what I'm saying. It's saying it's a Q factor of 94, and at 4 kilohertz is around where it tops out. You'd have to find it exactly, but right around there, it tops out at about 98. I think this is overestimating the Q, but I would suspect that it's right. And I mean, I don't think it's bad Q factor. It's probably like 70 or something. Maybe it's that high. I'd be really surprised. But not really surprised. I mean, I don't know what the hell I'm doing, but I would be surprised. What's my point? Is that I think the frequency where the Q factor is highest is probably correct. It's at right around 4,000 hertz. So now let's just wrap it up doing some back of the napkin stuff. So 4 kilohertz, high Q factor, 100. So I guess the very first thing to do is I'm saying I'm not going to glue anything down just because, you know, I just want this answer about adding flywheel mass and what that does. And is that like crazy, like, oh, it's fine, or is that crazy, like, you're an idiot? So let's figure out how fast the magnets are going at different RPMs. We have a 5-inch rotor, so equals this times times, I hope I get this right, yeah. No, I got it wrong. So if we take the 5-inch rotor and we times it by pi, then that gives us the circumference. So when this thing makes one rotation, it travels 15.7 inches. Let's convert that first to feet. Equals this divided by 12. So it travels 1.3 feet per rotation. So let's say that we're spinning at 1,000 RPMs. Then in 1 minute, this travels 1,308 feet. In 1 hour, this travels that many feet. 5,280, I think, is feet in a mile. I think it's right around there. So equals this divided by 5,280. Yeah, that sounds about right. So if you're if you're spinning at 1,000 RPMs and a magnet flies off, it's only going to be flying at 15 miles an hour. And we can kind of ballpark it. 3,000 RPMs, you would have a magnet hitting you at 45 miles an hour. So you want to keep it at 3,000 RPMs or lower. You know, we're probably not going to go above 1,500 RPMs for this. So you can see you know, it's kind of silly not gluing things in, but it's not entirely insane. I mean, the magnets might be going at like 25 miles an hour or something if we're really spinning it pretty quick. So let's wrap things up with what I think is the most interesting, and some of this was actually pretty surprising to me as well. If we think about Q factor, what's probably to me, the easiest and most useful definition, and that is the number of oscillations before the amplitude of the voltage of the oscillation is at 4% of its initial voltage. So in other words, it's basically the number of oscillations before the thing is damped out. Now, since we know that, and since we know that the actual number is 4%, we can kind of work backwards, can't we? So let's say that you had one oscillation. This is like an LC tank circuit, but the same thing applies if you're just cutting off the field after you've charged the magnet for a specific amount of time, equivalent to, you know, what would be a capacitor oscillating in an LC tank circuit. So in other words, a DC buck boost converter gets more efficient with briefer pulses as well. You know, again, until you run into skin effect or proximity effect, leave all that aside. So if you made it back 80% of the way to your starting voltage in one oscillation, how long will that oscillate until it gets to 4%? So we can take 0.8 and raise it to the 14th power, and there's 0.43. Let's say 0.8 to the 15th power, 0.35. So if you're going to get back 80% of your starting voltage, then you need a Q factor. You'll have a Q factor of about 14 or 15. Now in practice, you're going to have the voltage drop across the diode. Let's say you're hoping for getting back 90% of your initial voltage. What sort of Q factor do you need for that? Well, let's just double it, say 30. Yep. Or let's say 0.9 to the 31st. Same kind of deal. So if you're hoping to get back 90% of your energy sans the voltage drop across the diode, you need a Q factor of 30. Suppose you're hoping for 95%. So 0.95 to the 60th. Okay, 0.95 to the 61st. Still 0.95 to the 62nd. It's going to be about 63.95 to the 63rd. Yeah, so if you're going to get back 95% of your voltage, you need a Q factor of 60. Now this thing was saying a Q factor of like 90. So let's see, 0.97. It was saying like 90 or 100 to the 90th. Yeah, all right, 0.97 to the 100th. Okay, I'm trying to figure this out now. 0.97 to the 105th. Oops. Sorry. 0.97 to the 105th. Yeah, so to get 97% back, you need a Q factor of, what did we just say, 107. So what the long and short of that is that at around 4 kilohertz that we showed with the LCR meter, you're getting between 95 and 97% of your energy back, which you'd have a voltage drop across the diode, but if you ran that as a buck boost converter, it'd be 88-90% efficient is about the way I see that, unless you ran into other problems, with the core or something like that. So it should be theoretically possible to get 95% of your voltage right back, say into another cap, into another battery. Now, here's what I found interesting. Okay, bear with me here. So when we put it on the LCR meter, the highest Q factor for the coil that we wound was at approximately 4,000 hertz or 4 kilohertz. So that's 4,000 oscillations per second. So let's see if we can figure any of this out. Now, let's say you had a rotor with one magnet spinning at 60 RPMs. Then that would be 1 oscillation per second, or 1 hertz. But we're going to have 6 magnets, so that becomes 6 hertz. Right? If you had 60 RPMs and there was only 1 magnet, then it would only turn on and off 1 time per second, or 1 hertz. With 6 magnets, it would be running at 6 hertz. So that's kind of convenient that 60 to 6. But we can see that, since it goes from 60 to 6 there, in order to have that high Q factor, you would need to be running at 40,000 RPMs, which that I think before you got much past 5,000 or 6,000, the thing would just fly apart. So that's a no-go. Is there something else we can do? So that assumption is that you have a 50% on time and a 50% off time, just like an oscillating LC tank circuit or the oscillating signal they put into the LCR meter. What if we used pulse width modulation and your duty cycle is now only 10%? So now it's the equivalent of 6 RPMs being 6 hertz. because you're cutting off 90% of it. So now you only have to spin at 4,000 RPMs in order to be at your high Q factor point, and that's doable. So the final two questions are, how do you know what the duty cycle is? And the short answer is, I'm not sure, but I think you can just put it on the oscilloscope and eyeball it. And you know, if you see the thing on for 50% and off for 50%, then oh, that's no good. If you see more of a spike with about 90% off time, then you know that you're there. So you can do this where you get the high Q factor and you're spinning at a reasonable rate and getting a very efficient back pulse to go into batteries and whatnot. What's the drawback here? The drawback is that you have a pulse motor, and the problem with the pulse motor is it pulses and then it's off, and that's the whole point of what we're going to look at here in the next video is, does mass help to get through resistance during the off time? If you had a 50% duty cycle, it would only be off 50% of the time. If you have a 10% duty cycle, then it's going to be off 90% of the time. So your torque is going to go, you're going to have very little torque. Now, you could get around that by having 10 offset rotors that go at different times. So there's never a time where it's actually coasting. There's always one that's blinking on and off, and that'll be the topic of a future investigation. It would have been nice if you could have it at 50% on, 50% off, and then you only need two offset rotors two offset electromagnets to have the thing on 100% of the time. But this is what I'm seeing with the coil. But we now know that for that particular coil, you would want to run it with 10% duty cycle, approximately 4,000 RPMs, in order to get the highest Q factor. So that, I think, is kind of cool if that holds up, and that'll also have to be investigated. But I've talked at you more than enough. In the next video, we'll spin and we'll add mass and we'll take away mass, and we'll see what happens in terms of the RPMs under load, with and without mass. But for the moment, with apologies to the Dixie Chicks, we're ready to run. All I want to do is have some fun. Copyright strike. Anyway, we're ready to run, and that'll be the next one. You can actually see something spinning around and not have to listen to me yabbering away at you. Stay healthy, keep smiling. Talk to you later. Bye.